So in this class I'm going to teach about I2C programming. So here we will send data from ARM to this DS1307 real-time clock through this SG line. And in before code, in the last code, I thought that we call the byte that byte write functions, and we send data by calling that functions every time. But here we will do the brush write, and so we will call the function only once, and by giving the slab address and the first memory locations of the RAM chip inside that slab device GS1307, and after that we will write byte continuously in those memory locations. Okay, so let's write the code. We are going to send the time and then all those three values that and then we will send to this date, day, year, and time. Let's send this. So this code is similar to the before code, so let's write the code so that it is handy. Include I'm writing the library of the Java ARM4 based microcontroller, and then define the slab address. We define the slab address as 0x68 as usually for GS1307, and then write the I2C initialization functions. I will explain this little later. Brush write, we are going to do brush write. Here we will pass slab address and then memory address, and count how many byte we are going to send the data byte, and then we are going to pass the value of data to the pointer. And I will explain this address also, this function also a little bit later. So let's come to the main function first, because explaining this will jump to separate idea, and it will be not going in the flow because of that. And so this is the main functions. Here we will just take array of name, we will take that value. This one this one is for second and minute. You can set any value. you can set any value and then okay, let's copy all this. Here, okay, this is 55 seconds, and so okay, the hex value will be 0x55. Okay, here it is, and this 55 second hex value in binary, it is written like this. Okay, and so it will be sent bit by bit through the I2C bus. In that way, 58 minutes hex value is 0x58, and the binary value will be written like this. This is 5101, so this is 5, and 8 is 1000. Okay, so it is 1000. Here also 13, okay, hex value is 1x 0x13. This is 1, so it is written 1, and 3, okay, it is 1 1. So okay, and that means Sunday is 0x01. If that is Monday, then 0x02, count like that. Okay, 14 is like that, June is if this is January, then 0x01, February, then 0x02, so this is June, so it will be 0x06. And this only the last 2 bit 2 digit is will be stored in the memory of DS 1307, that real-time clock device which we use as slave device. So okay, here it is 0x26 because the only last 2 okay digit will be stored. Okay, so 2 is 10 and 6 is okay 110. So in this way, okay, data will be sent bit by bit. Okay, I'm just saying so that you doesn't confuse. Okay, you can change to any okay whatever you want. 13 hours here I'm writing. You can change to whatever you want. 9 okay hours. Okay, you can change to Monday, Tuesday, whatever. Okay, July, August, September, any years. Okay, will be okay, and then transfer to this particular all those okay address. It's specific. Okay, this second is if any value sent here, then it is for second. Okay, specific means second, for second, minute, and hours, day. Okay, like that. I'm just saying so that you doesn't confuse. Okay, this is the main functions. We are just taking an array called time data set of 7 values, and this is the values that we copy from these values. Okay, this whatever you want to set, and these values okay written like this, the hex value. And here I want to okay, call the initialization functions, I2C initialization functions. So let me write this I2C initialization functions and explain it. This is simple. Okay, I have explained in before code also, so just write it. okay. System control is using I2C GPIO equal to 0x. Let's make it, okay, let's choose GPIO A. This system control CTL, okay, this system control is choosing this particular register RCGC GPIO, that 32-bit register. What this register says is supplying clock source to the bit 0 to 7 of this resistors, okay, of this 32-bit resistors, to choose a particular port. So okay, this is 0 is this to the bit, okay, so this is 1, and so in total this is bit 7, so we are setting 1 to the bit 0, that means we are supplying clock to this bit 0 to choose, that means we are choosing port A. Since we have choose port A, let's choose other for our program. So so system control is okay now using this resistor, and this resistor says to choose to supply a clock source to a particular bit of this resistor from 0k to 3-bit to choose a particular I2C version you want to use in your code. So we are supplying 0x02, so hexadecimal value is 0010, so it will be 0010. You write 1 here because there is 1, so you are setting the I2C version 1, and so you are okay you can use I2C 1 in your code. And then since we are using the port A, that means GPIO A, GPIO A, so this is C is right, C is this and 0 is this, okay. So alternate function means we are okay in this port A pin, we choose any pin, okay, we choose any pin, and then particularly we choose bit 6 and 7 for in I2C, and we choose this particular pin 6 and 7 because for alternate function means okay that we can use for any function for any operation for I2C, SPI, UART, anything, okay. And we are choosing only 2 pin, okay, because one is for SCL and one is for ST line, okay, and we need only 2 line. I2C is a 2 line bus, so because of that. PCGL this, okay, what does this means? This means clear, okay, this bit, okay, this bit. Why only this bit? Because we have chosen this bit 6 and 7. So this bit 6 and 7 will be clear, and so that there is no dummy data, so that it can be used as fresh input. And why this one PCTL is written here means it is connected to we are clearing this particular bit for to operate the function of this PCTL. And so the next line will be, as we are going to as we clear this particular bit to operate the function of PCTL. So next line we will configure to that particular bit the value we are clearing this bit so that we can set this bit values this bit values in PCTL as 3 and 3, so that this particular first bit is set for I2C SDA, and this 6 bit is set for I2C SCL. If we set to this register bit 7 the value 3, then this pin will be for this pin will be for SDA I2C, and this pin will be for I2C SCL. For others it will be different values. For example, if we want to set for PWM pulse width modulation, then this value will be different. So according to the value set by this port control register, we are setting it, configuring it as 3, so that it is used, that bit is particularly used for only I2C. (0xC0). 0xC0 means we are setting this pin as digital. C is 1100, right? As a hardware engineer, you will become one day hardware engineer. So you have to know all of this. So C is 1100, and this is the 0 is 0000. So just setting this two particular pin as for any digital operation as digital pin. GP means right, it is 1000 in hexadecimal. So this only this STL line is set for is configured the ODR circuit. I mean the ODR is applying to this pin 8 because that means it means the SDA line, that is is connected, SDA line is connected to a circuit, the device, okay, and this device output will be connected to a low level function transistor, because in open drain system, this is open drain system, ODR, and all the device should be connected its output to a low level function transistor, because sometimes the I2C bus is allowed to access and or share by some master. At the same time, in some rare or exceptional case, at that time, if some master output circuit is connected to high level transistor function, high level function transistor, or some other connected to low level function transistor, then sometimes this high output of some device may flow to the low level output of some other device. So circuit may happen, and because of that, it is prefer only low level transistor output circuit of the in the device. So because of that, X10. So here we are choosing the device to operate as a master. By setting the bit D4 to 1, we are choosing the device to function as a master by enabling master function enable bit, that is D4 bit to 1. To function as in master. Again, this is very simple things in most program. You will use this bit only to set that device function as a master. And then my bad. And MTBR equal to 7. So MTBR equal to 7 means the data transmission will be carried out with a speed of 100 kilobit per second. So this is initialization functions of I2C. We support the port. We support I2C. We choose the port. We choose the I2C versions. We make the pin 6 and 7 for alternate to work as perform as alternate options. For alternate options, that means for alternate means for many there is many choice where it can operate as. So then we can set it for any of the UART or I2C or SPI or many. So that particular pin, we clear it so that there is no dummy data to be connected to some particular functions of this resistor. And why we clear is we want to in this same resistor, we want to set the value to 33 so that this particular pin is initialized for I2C, SDA and for SCL only. And then we are setting this 2-bit, that is 6 and 7, that is this 2-bit as digital. And ODR means we are setting only the data bit as a low level circuit device output. And then choosing a particular device as master by setting the bit default to 1, and then data transmission at the speed of 100 kilobit per second by putting MTR equal to 7. So initialization process is finished, and then let's write the code of sending address bit and data bit byte by byte. So we are using brush right here. I'm going to send slab address. I'm going to send memory address. I'm going to count how many bytes to send, so byte count. And I'm also going to send data to the pointer. And so we check just one variable and error, and then if byte count less than, if byte count is less than 1, then so if byte count is less than 1, then there will be no byte count, right? So here we will say return -1. That means stop the process. And if there are data to send, then data to send, so I2C1 will use this MSA register to store the address of slab device. And here we will choose a particular so there are so many data to send. Then we will choose a particular slab device by writing the slab address. That means writing means transmitting the slab address in the bus. We will choose a particular slab device, and since slab device is only 7-bit and it is stored in the bit 0 to 7 of the I2C MSA register, so it will be stored in 1 to 7 as it is 7-bit only, and 0 is used for other functions to detect whether we are receiving from the slab device or transmitting to the slab device. So the slab address is used to store in the bit 1 to 7. So it is not stored in the bit 0. So as the slab address is 68, okay, in our case, so this is 6 and this is 8. So we will write 0 here because it is stored from bit 1 to bit 7 only. So we will shift, okay, we will shift to left only one times, so that it was not stored in, okay, bit 0. It is stored from bit 1 to bit 7. So we are saying this is left shift. We are shifting to left only one times, so that bit 0 is not used and it's stored from bit 1 to 7. Then, okay, we will, okay, store in the MDR, we will store the memory address. First, this one is first memory address of the RAM inside the slab device GS1307. And this address usually start from 0x00. Okay, as we can see in the here, the address start from 0x00 and then consequently increasing to, okay, 1 2 3 4 5 6, okay, up to it is there is in total 64, okay, 64, okay, bytes, and one address, okay, that means one address 0x00 is for one, okay, byte location. Okay, then I2C 1 implies MCS equal to 3. So we will, okay, the 3 is 0011. So 3 is 0011. So it means, okay, run and then stop. As we are transmitting, okay, to the bus, that means writing. Transmitting means writing or sending. So we are writing. So because of that, we are using this MCS register as write control register. Okay, write control register. And since we already wrote that slab address and memory address in the program, okay, we want to start the transmission, so we are choosing this particular bit, run and then start to start the transmission. Okay, after, okay, starting the transmissions, after starting the transmission, here we are, okay, start, then this address is going to send. After we are starting the transmission, okay, let's write the code first. So this is starting the transmission. That means the bus will be busy, right? So error equal to I2C 1 with 2 done. Okay, so in this function, obviously you know that the bus will be busy as the transmission is already started by this bit 1 of MCS resistor used as write control resistors. So we will write the functions I2C with tildes. So as the transmissions has already started by this bit 1 of MCS resistors used as write control resistor. So as the transmission is started, the bus will be busy. Busy means transmission is going on. So while the bus is busy, that means I2C1 implies MCS and 1 means bus is busy. Here bus is busy means we are here you are noticing the bus is busy. Noticing means you are reading the bus is busy. So you are noticing the bus is busy, you are reading the bus is busy. So you are now using the MCS resistor as read only control resistor. And so we will check if the bus is busy. Well, that means transmission is going on, and in transmission is going on at the time you want to check if any error is pop out or not. And also while transmitting, you are sending address, right? So in sending address, you want to check you need to check the acknowledgement bit. So in order to check this acknowledgement bit, you need to know whether this acknowledgement bit is set or not. But here you are sending address, so this you want to know if this acknowledgement bit, address acknowledgement bit, is set or not. So you're checking if there is any error or not, but error is usually caused by address acknowledgement bit or data acknowledgement bit. So better we check all these three, because this three is always together. This error is usually caused by address acknowledgement bit or data acknowledgement bit or by address acknowledgement bit. So we better check all of these three, and not all of these three, but usually we check this bit together always. Better because the error is caused either by these two. So better check these three. So, and because of that, so the bus is busy. One is busy. So MCS value is now 1. So the bus is busy. While the bus is busy, return I2C 1 implies MCS and 0x E. So checking the address acknowledgement bit by checking the data bit, address acknowledgement bit, error, E means 0. So we are checking only we are focusing on only this 3 bit, but here we are sending address. So this is address acknowledgement bit, so we are focusing in this, and we are not sending data here, so we are focusing only on this address acknowledgement bit. And if address is acknowledged, that means the select device is ready to receive the data that will be sent by the master, then this address will be acknowledged. And if address is acknowledged, then address bit will be 0, and if address is acknowledged means error will be 0. Then this that 0 bit busy bit we are not checking, so it will be 0. And if there is error, then data acknowledgement bit we are not checking here because we are not sending data, so we are sending only address, so address acknowledgement bit will be checked. And if there is error, then it will be address is not acknowledged, then 1. Then so address is not acknowledged, then there is error, so error will be this, error will be set to 1. And this the next bit is busy bit is not checked here, so it will be 0. So if there is any error, then this bit will be returned, and if there is no error, then this bit will be returned. So while the bus is busy, we are checking if the address is not acknowledged by checking the error the error bit and the 2 bit that usually cause error. So if there is error, then return the error. And so we have send the address, and after this we will write or send the data. So if byte count greater than 1, so if byte count greater than 1, then we will write while loop. While byte count greater than 1, if there are so many data to send, then I2C 1 implies MTR, where data will be sent, data plus So okay, this is data pointer, and it is incrementing. So okay, the data store in the bit 0 to 7 only in this register. After sending this, then data pointer will point to the next data that will be stored to this register. Okay. And after this, write MCS equal to 1, and so okay, here what we are saying is I think it's better to write this 5, because here we are going to send data, and data will be for the first time we are sending data. So we will check, we will make the process to run, and because it is the process is going on right as the address is acknowledged. So here as the address is acknowledged, data is in the is in the process of sending. So let's make this one only run, and then so after this we will and that data is transmitting, then the bus will be busy. So the bus will be busy, and we are checking the data so far sent is acknowledged or not. Likewise, we are checking if there is any error or not. So the bus will be busy, that means data is transmitting, and we are checking if there is any error or not by checking this bit, data acknowledgement bit. If there is error, if data is not acknowledged, then this data acknowledgement bit will be 1, and we are not checking address because we are not sending address here, so it will be 0, and as address is not acknowledged, then error will be 1, and then we are not checking the busy bit here. So if data is not acknowledged, that means the slave device doesn't want to receive any data, then this error will be returned. And if there is no error, that means data is acknowledged, then this data bit will be, data acknowledgement bit will be 0. They are not checking address, so it will be 0. As data is acknowledged, then the error will be 0. Error will be 0, and we are not checking busy bit here, so it will be 0. So if there is no error, this bit will be sent, returned, and if there is error, this bit will be returned. So here the data is sent, it is run, the process is running, so data is sent, and then the bus is the process is running, so the data will be sent here. The bus will be busy and checking if there is any error or data is particularly checking if there is any error. Okay. And the bus is okay. Meanwhile, the bus is busy, and then after this we will check the that I2C implies zero x 4 0. Okay, and this is the bus is busy, and this line is checking if the and this one is for transmission is complete, and let's not write this. And if any error, then if any error, then return error. I'm not writing that line because I don't want to complete the transmission still now. I just want to separately check the last byte again. That's why. So so if any error during the busy transmissions of bus, then return. Okay, and then let's byte count, and then we are decrementing the byte count. Okay, and this I want to if there is error, then return the error, and the process will be stop the transmissions, and then decrease if there is no error, then reduce the byte count by 1. Okay, so the process will be like that until the last byte to be sent is left. And then after this we will write oh my god. Where is that? Okay, and then after this we will so only one byte is left. Okay, so this one this loop will run until only one byte is left, right? And then the last one, I2C one in MDR is the data that is the register that where we store the data to be transmitted. So MDR data plus, and then I2C1 implies MCS equal to here, let's write 3. 3 is saying that since we are going to transmit, that means we are writing, we are using I2C MCS register because we are writing, and so we are using this MCS as write only control register because we are writing, we are transmitting, we are sending, because of that. And this 3 says run the process. The process is running, and after sending that byte, stop the process. So and then here I2C1 wait to done. Wait till done, that is the bus is busy, and that means the byte is sending, the last byte is sending, and we are just checking the data bit, if the data is acknowledged or not, like that. And if there is any error, and while zero x 40 is 4 means right, and 0 means right. That means it is the 6-bit. And this 6-bit, the bus is busy here. And this MCS and 0x40 means this is the 6-bit. So here in this line, we are just checking whether the transmission has over or not. We are checking. That means we are reading. We are reading, that means we are checking. So we use this bit MCS register as read only control register because we are checking here, we are reading here. So we use this busy bit. This busy bit is used to check whether the transmission is complete or not. When this busy bit is low, then the transmission is complete. So that's why when the busy bit will be low, surely after some time, so the transmission will be complete at that time. So that's why the bus is busy here, and here the transmission will be complete after some time. But this busy bit, when it is low, the transmission is complete. But when the transmission is complete, the program should check the error bit. Error bit. The program should check the error bit, and then this address acknowledge or data acknowledgement bit will be set. Will be set. So error should be checked and should be set to this address or data acknowledgement bit. So let's write the next line of code. So this error should be set to that address acknowledgement bit, that is MCS and 0xe. So because of that, I2C1 implies MCS and 0xe means e means what? E means data acknowledgement bit, address acknowledgement bit, error bit. We're checking that. So we're setting it to address acknowledgement bit or data acknowledgement bit or address acknowledgement bit, as it is told to set the error to the program should check the error bit and then set to address acknowledgement bit or data acknowledgement bit. So we are just setting the error to this, because if there is error, it is stored in this variable, and so this variable, if there is error, then we are setting to that data acknowledgement bit or address acknowledgement bit. So if there is error, return the error and transmission is over. If no error, if there is no error, then return 0, that means no error. And so in the main program, this one is in the main program, what we do is we just take array of 7 values. These are the values we want to set for all those second, minute, and then time, etc. And this one is for all those values, that month and year. So after this, we just take an array, and after this we are going to send this value. And after this we just want to initialize the I2C. So we call the I2C initialize functions, and after this we want to send the data, so we call the that I2C function to send the address and data. Burst rate. And in this burst rate, what we are going to do is we will slab address, because there is only one slab address. And so it will be but here we are going to call the functions. The burst rate means we are going to call these functions only one time. So the burst, this is slab address, and then after this we need to give the first memory location 0, and then the byte count will be how many? It will be 7, and then we will time that to set. This will be, we will give only first is we will give 7, so that the all the values will be call. Okay, and so in this way we will write like this. And after this, what we have to do is we will make to operate for loop. I think it's there, but just make it run an empty loop. An empty loop, for loop, because after writing this function there is something in the I'm calling this function, but there are many things going to work behind. The main function is going to call this function, and then all those slab address value is going to initialize, and then send this address to that through the I2C bus, and all those memory address is going to initialize by passing to that by calling that burst write function, and all those this value byte count is going to pass in that functions, and then all those steps are going to execute step by step. So behind so many work is going to operate. So because of that we are just making this for loop to run, so that the system is not stop immediately, making it all the background functions to operate, and like that. So so in this way we will write the code. And here what will happen is that in this lab address this will be only one time, as we are choosing only one slab address, and this one is the first memory location, because in the burst write it says we have to give only the slab address and then first memory locations. And after that the whatever values that is we are choosing here, whatever values that we are going to through this array will be sent one by one. Will be sent one by one through the I2C bus to this address. And then first of this address, and then continuously to this address, as the burst write says only the first address will be give, and then the consequent address will be automatically incremented by the I2C bus. Okay. So thank you all for this session.